Hello, everyone. My name is Corbin, and I will be opening our group presentation on student engagement dataset and its role in learning analytics within higher education. This study highlights the rapid expansion of distance learning since the early 2000s, driven by widespread internet adoption and advancements in digital technologies. As educational institutions began recording and storing learning materials online, e learning environments, commonly referred to as learning management systems or LMS, and virtual learning environments or VLEs became increasingly central to higher education. As we all went through the COVID-19 pandemic, this time significantly accelerated this transition, forcing institutions worldwide to rely heavily on the LMS and VLE platforms. During this period, usage increased dramatically compared to the pre pandemic era. However, the shift to fully online also exposed challenges, particularly reduced student engagement and lower overall satisfaction in online courses. In response, the authors positioned learning analytics as a key approach for understanding student behavior in online education. Learning analytics examines the relationship between student interactions, academic performance, participation levels, and attrition rates. Its goal includes its goals include explaining learning behaviors, increasing student success, improving retention, and also identifying at-risk students. In doing so, learning analytics supports broader institutional goals such as improving academic outcomes, enhancing student persistence, and promoting evidence-based decision making in higher education. The study emphasizes that engagement extends beyond simple clickstream data. It also it includes assignments, quizzes, form participation, timing of submissions, relative activity levels, and overall interaction patterns within the learning environment. Because there's no standardized consensus on how engagement should be modeled, and because existing public data sets are limited in scope, the authors argue for the development of a more comprehensive data set. For this reason, the Student Engagement Dataset, or SED, was it was constructed to use the data from University of Malaya's Moodle-based virtual learning environment to provide a structured and statistical and meaningful representation of student engagement in the higher online education. With this, the next section will explain the methodology used to construct the dataset, including data extraction, cleaning, and feature engineering.
Methods. In this section, I will present the method used to construct the student engagement dataset. The objective was to transform raw learning management system activity data into a structured and anonymized dataset suitable for analysis. The methodology consisted of the three main phases: data extraction, data cleaning and anonymization, and finally data aggregation and feature engineering. All processing was implemented using Python libraries including NumPy and Pandas. In the first phase, raw student activity data was extracted from the model learning management system using PostgreSQL queries. Grade data was retrieved separately into CSV format. The researchers selected only engagement-related activities such as logins, quizzes, assignments, forum interactions, and attendance. The dataset was limited to one academic semester to maintain consistency. In the second phase, the dataset was cleaned to remove missing values and inconsistencies. Only records within the semester timeline were retained. Non-student users such as faculty accounts were excluded. Grade values were standardized. For privacy protection, all personal identifiers were removed and replaced within the anonymized IDs. This process complied with institutional data protection policies. In the final phase, over 12 million logs records were aggregated into meaningful engagement features. These include total logins, time-based login categories, assignments submitted, quizzes attempt, and file downloads. Engagement metrics were normalized by the number of courses taken to ensure fair comparison between students. The final output consisted of 4 structured CSV datasets ready for statistical analysis.
My name is Hayden Blue, and in this section, we will be discussing data records and analysis. We will begin with the architecture of this massive data set extracted from a Moodle-based learning management system, or LMS for short. There are 4 core tables in this database. These tables are linked by a randomized and anonymized user ID. This allows us to track a single student without compromising their privacy. The purpose of this database is to bridge the gap between a student's academic performance, such as their grades, and their actual learning behavior, such as every click or log on within the system. As we move through the next slides, we will see how these 4 tables work together to paint a picture of a student's engagement. Let's take a look at our first table, Student Grade Detailed CSV. This is our most granular look at academic outcomes, containing over 90,000 rows that cover 2,407 unique courses. For every student, we track their course ID, faculty, and the final mark on a standard 0 to 100 scale. Statistically, the results were quite positive. The median mark across the university is a 75.0, with the vast majority of students receiving grades in the A minus to A range. The data also shows that courses labeled university, which are your general subjects that are common across all facilities, contribute significantly to these high medians. This is likely because they have a lower complexity than the core specialization courses you'll find in computer science or chemistry. Let us move on to the second table, which is the student grade aggregated CSV. The purpose of this table is to help us understand the student workload at this university. This table captures performance data for 16,909 students and specifically looks how many courses they've completed and their total marks. The workload distribution tells us that most students at this university are balancing 6 to 7 courses per semester. However, we do see a wide range of paths that students are taking. Over 1,200 students were focused on just one single course. This was likely final year students just completing up their last requirements, while a small group of 63 students tackled 10 or more courses at once. Moving on to the next table, which is the student log CSV. This is the most extensive file containing over 12 million rows of raw interaction data. This isn't just about logins, it records every single specific click, tracking 36 unique LMS components and 37 different types of actions, whether the student was viewing a resource, submitting an assignment, or starting a forum post. The key attribute here is the time created timestamp for every single event. By analyzing these timestamps, we can see a literal pulse of the semester. One of the most striking temporal insights is the dramatic drop in activity during semester breaks. This allows us to map student engagement against the academic calendar with high precision. This final slide focuses on the Student Activity Summary CSV table, which serves as the consolidated analytics view. The dataset integrates aggregated behavior logs with performance metrics into a structure of 16,909 rows with 20 specific columns. Engineered features provide a deep dive into when activity occurs by grouping logins into 4-hour intervals, such as midnight login, which occurs from 12 a.m. to 4 a.m. To ensure a statistically fair comparison, all activity metrics, including the number of assignments, quizzes, and file downloads, are normalized by the total number of courses a student completed. Normalization prevents students with higher workloads from appearing more engaged simply due to the volume of their requirements. Statistical analysis of these summary features indicate that peak engagement occurs at midnight, followed by afternoon, then early morning periods. These patterns suggest a more substantial portion of student interaction with the learning platform happens outside of traditional classroom hours, particularly late at night.
Hello, my name is Jason Hartz, and I will be giving the next part of this presentation. In my part of the presentation, I will be discussing the section 4 of the paper of student engagement data set, and that specific section deals with the correlation analysis. And specifically, what we're trying to do here is ask or answer the question whether students' behave online actually predicts how well they perform academically. Now, before diving into the numbers, it helps to understand why the researchers chose this approach and how they set it up. The core research question is simply do things like logging into the LMS, submitting assignments, and taking quizzes actually correlate with better grades? Now, the researchers couldn't use just a standard Pearson correlation. Why is that? Well, when they did the data distribution using QQ plots, which you'll remember from earlier part of the paper, they found that most of the engagement features are positively skewed and non-normal. That would mean that Spearman's rank correlation is the right tool because it doesn't assume normality. So they did two types of analysis, one using all the 16,909 students in the data set, and then another one that dealt with the top students. And now remember, top students were defined as those with an average mark of 90 or above. So roughly about a group of 172 students. This lets them ask, does engagement relate to performance differently for high achievers? Now, starting with the full data set of nearly 17,000 students, the result is that every single engagement feature showed a Spearman correlation of less than negative zero point 0.1, and every single one was statistically significant with a p-value below 0.05. Now, at first glance, that sounds impressive, but there's an important catch, and this is actually one of the paper's most insightful points. With a sample size this large, even the tiniest real world effects will appear statistically significant. This is known as the large sample effect. The researchers used Spearman's correlation specifically because the data is non normal, which was the right call. So, what's the bottom line? The correlations are statistically significant but weak to negligible in practice. The conventional threshold of a strong correlation, which is above zero point 0.5, these results don't come close. Logging in more, viewing more courses, and spending more assignments, none of these strongly predict a student's grade when you look at the full population. Now, things get more interesting when you zoom in on the top students. With this smaller group, again, about 172 high achieving students, the large sample effect disappears, so only genuinely meaningful correlations will survive the significant test. Looking at the table, you can see that out of 18 features tested, only 3 reached statistically significant at the 0.05 level. Now, here's some points. Number of courses had the strongest correlation at 0.22. Top students who took fewer courses tended to score higher. If you look at early morning logins, logging in between 4 and 8 a.m., that also correlated negatively with performance. And last, the number of assignments submitted showed a similar negative relationship. And here's the key interpretation the authors offer. There are all negative correlations. Top students who do less of these things tend to score higher. That points toward a really interesting conclusion. Quality of engagement matters more than quantity. A student cramming at 4 a.m. and submitting many assignments might actually be struggling, while a top performer is more strategic and focused. So, what does section 4 leave us with, or what is the correlation analysis main points that want to get across to the reader? The first is that quality beats quantity. The evidence from top students suggests that doing more on the LMS doesn't necessarily lead to better grades. It's more about the purposefully how you engage. Second, the correlation throughout are weak. No features exceed a correlation of 0.22, which means LMS activity alone is a poor predictor of grades. Academic performance is shaped by many things the dataset doesn't capture: prior knowledge, study habits outside the LMS, and course difficulty. Third, and perhaps the most important for anyone using this dataset, don't confuse statistical significance with practical significance. The author recommended policymakers set much higher thresholds, say having a correlation 0.7, before drawing conclusions that affect real decisions. And then the last point to bring home is this analysis opens the door for richer future work: early detection of at risk students, modeling procrastination, and understanding what actually drives engagement in high performing courses. And with that said, I want to thank you for your time, and I will move on to the next section.
Okay, in this final section, I'll discuss the usage nodes, limitations, and broader role of data analytics in the field of higher education, using the SED dataset from our article as an example. So from a technical perspective, all processing in this study was done using Python, NumPy, Pandas, and Jupyter Notebook. The researchers extracted LMS data, structured it into CSV files, cleaned it, aggregated it, and then performed the analysis. Many studies have used machine learning to model student performance, but this study prioritizes building a structured data set and understanding engagement patterns first before applying those predictive models. In this study, educational data is described as raw but clean. This means the data has been cleaned, but it still reflects real-world student behavior. It's also important to note that outliers and zero values are inevitable. For example, some students log in hundreds of times, while others rarely log in at all. Additionally, many engagement features are skewed. In this study, most students cluster around lower or moderate activity levels, while only a small number of students show extremely high activity. Finally, most engagement variables are non-normal in distribution. Another insight from this study is that certain LMS features are very much underutilized. Forum activity accounted for only a small percentage of total log data. Most student interaction instead consisted of viewing materials, downloading files, and submitting assignments. These findings show how analytics can help reveal behavioral patterns and not just final grades. There are also important demographic and structural limitations that exist in any higher education analytics study. In this data set, some limitations include the fact that nearly 90% of students were Malaysian, and there's no metadata available for gender, age, or socioeconomic background. More broadly in the field, many studies rely on small samples, sometimes ranging from even about 50 to 3,000 students. They may also include only a limited number of courses, sometimes even as few as one course. Study durations also vary widely from a single semester to multiple years. The SAD dataset attempts to address some of these limitations by providing over 16,000 students across more than 2,400 courses, and while also using data from just one semester. But even so, it still had its own demographic limitations like any other study. And because of this, predictive models built from the dataset may or may not generalize well to other populations. So that shows that it's worthwhile for institutions to conduct internal data analysis of their student populations. Ultimately, in higher education, data analytics can be applied by structuring and analyzing LMS data to uncover patterns in student engagement and performance. The goal is basically to support early intervention, improve course design, and guide evidence-based institutional decisions.